All right, so in this video lecture, we are going to look at an application of the definite integral, where we're going to apply our understanding of definite integral into finding volume. But the volume here, we're going to calculate the volume of any solid by breaking that into slices. That's why the title here is that we're going to calculate volume by slices. Okay, but at this point, it's probably not very clear what it is that we're going to learn how to calculate volume of a solid by slices. Okay, we're going to apply our understanding of calculus of the definite integral into calculate the volume of any solid by slices. But so at this point, it's not very clear. But after a few of my explanations that follow, then we will have a better idea of that. Okay. And so this video lecture here is highly recommended to be viewed after you have understood what a definite integral is. And so find my video lecture on what a definite integral is. And it's also best to view this video lecture after you have learned what the fundamental theorem of calculus is. So also find my video lecture on the fundamental theorem of calculus to understand how we can operate in general with any definite integral. And then this problem here, this lecture here specifically, is how we apply that into calculating volume of any solids by slices. Okay, so now let me erase the title because I need a lot of more space here, and let's bring up the actual problem here. The idea of calculating volume by slices is, and it's gonna actually be a shock that once you realize the existence of these solids out there in our daily life. I challenge you. I issue this challenge to anybody. I mean, you go out there on the street, you will see randomly here and there a solid, an object that has volume where you can calculate by constructing the slices. Okay, and so let me first explain what it means by we're calculating volume by slices right here. So think about there a few times we're gonna have a solid like this. Let's say I'm gonna draw a region right here. Just for now, just draw a region, oval shape or whatever, just a region. Okay, it could be also rectangular. Could also be a rectangular, and then or maybe in 3D view, that rectangular view is like that. Okay, but the fundamental idea now is that, you see, think about if we're sketching the area inside of that region. This is naturally what we do here. It's things that we have been doing for years prior to this point, but now I'm going to try to make it clear that we're going to be even more aware of what we have been doing. Okay, so for a region like that, or for a region like this, or any region, if I'm now asking you to make the sketch of the area filling in that region, then here's how we sketch. Don't we draw these stripes like that? Okay, that's how we're sketching the region, the area in the region. So after making a whole bunch of stripes like that, or slices like that, right? So I'm starting to get to that term slice like that, but right now I'm talking about we start out with a flat base region. So just like that, the region can be an oval, the region can be a rectangular shape like this. Okay, and so sketching the area, right, shading the area, we're going to be as at our best, and even children know how to do this. Okay, we're creating those stripes. And I'm not saying that the stripes have to be vertical or horizontal. It's pretty much our choice. Okay, and so the same with this, we can sketch our stripes like that. That's how we sketch the area that's filling in a region. And now those regions, this is not what we're talking about. We're not only talking about these regions. We're just looking at these regions, and I have to start back from the ground. That anytime that we're filling in the area, we're shading the area of that region, we naturally tend to use stripes. But now furthermore, I want you to understand a little more. See, I've been doing this for years, and even children can do this. But the idea now is that intentionally behind the scenes, subconsciously, our mind is telling us that we're making these stripes to be parallel. See? And I'm not doing the best job right here in terms of doing parallel, but these are meant to be parallel shading. Parallel stripes, okay? Parallel stripes and parallel stripes right here. So these stripes, and still we're on that flat surface of that base region, right, the base area, okay? But now think about these slices right here, these stripes right here being parallel. So that's a key in the key thing right here, the stripes. Okay, and of course now you understand what I'm talking about. The stripes on the base region are parallel. Okay, that's one key characteristic of those of these pictures that we're constructing, that we're about to build right here. And then now on these, think about these, and so now I'm only, and of course being a human being, I can only draw a few countable number of stripes here. But then yes, they all have to be parallel. See, doesn't matter which way they go, and they can go quite tilted like this, but they all have to be parallel. Stripes are all parallel. But now on top of that, think about this region. So another thing to realize, another realization that I need to point out right here is that the length on each stripe here, as we stripe through the region, as we are sketching that area, as we're shading through the region, each stripe here at any instant, each stripe has length determined by the boundary of our region. So our region here decides or determines how long that stripe is. So some stripe is shorter than some other stripe. So the stripe here has variable length, has changing length, depends on where we put the stripes. But once again, these are all parallel stripes. Okay, and so now from that idea right here, think about on top of each stripe, I'm going to put a picture. So, and each stripe here is meant to be straight. That's why it's stripe. Okay, and now on top of each stripe here, I'm going to try to draw a triangle. So here I have a triangle. It could be this triangle here, could be an equilateral triangle. So this picture here is just a choice. Equilateral triangle. So at that, okay, so I'm putting an equilateral on that stripe here, and then at different stripes, I'm putting another equilateral triangle. And think about it, equilateral triangles are standing vertically up. So from where the stripe is, right, the equilateral is being erected vertical. So think about if this region here is on the base where you're looking straight at it, and now you have to start turning your viewing sense into a 3D perspective like that. Okay, and so just try to view this area here as some sideways flat area that your eyes is looking straight at it. So kind of in a 3D view, that's how it is. And then as I'm shading the base area here, the base region here, then I'm using parallel stripes. So we're clear with that. But now on each stripe, at each stripe, I am going to erect a shape. Okay, and so now equilateral triangle is just one shape of among infinitely many choices out there. So we can also erect a triangle. I mean any regular triangle, or just I mean the more regular it is, the better it is. So how about a rectangle over that, for example, or a squares over that, right? So these are regular shapes right here. So equilateral triangle is just one shape among the choice. But now, since I chose equilateral triangle to be erected vertically from this ground right here, from this base area right here, then think about the impact. I said earlier that each stripe, at any place where we place a stripe, the stripe has a different reach to a different length. And then the length there becomes one edge of our erected equilateral triangle. And think about if we're looking straight at the equilateral triangle, then one major characteristic of an equilateral triangle that anybody know, even children know, that the three edges have to be equal in fundamental Euclidean geometry. And that means the triangle here will scale big or small depending on where we put our triangle, our stripe. Because maybe this stripe here has the longest length, then the triangle gets to the biggest scale. But then compared to the same equilateral triangle but placed at a different stripe, then that stripe gets smaller. So, or for example, when we're looking at the triangle, the equilateral triangle at this point right here, then the triangle here looks really small, but in the end, these are all equilateral triangles. So the scale of the equilateral triangle, my point now is that the scale of the equilateral triangle gets big or small depending on where we place our stripe, or depending on where the triangle is at, on which stripe that is. Okay, because again, the stripe is changing its own length, okay, and so its own length determine how big that equilateral triangle is. But now in the end, think about if we can achieve all equilateral triangle, okay, on this all equilateral triangle, okay, and of course I'm only a human being, so I'm not the best at drawing all of these. There are students of mine in my past quarter drawing pictures at 10 times better than mine. Okay, but we having pictures like that. Okay, so gladly in these days we have technology to fulfill this need right here. So let me bring a copy of this. Okay, bring a copy of this on the computer screen so that you can see what I'm talking about. All right, so there is my shape. So this is the best my technology that I'm using can do for me. So as for now, I ask viewers or students of mine not to worry about this, what these g of x or f of x are all about. We're having a region here. So that region looks like the shape I was drawing on the board earlier. Okay, and so there's my region being it could be an oval, and don't even have at this starting point right here. No one needs to worry about what equation is this. That's not the point. But now, as I was saying earlier, we're going to construct an equilateral triangle. And so let me quickly put up the equilateral triangle. And in the end, the software I'm using here is still quite limited. So but that's the best I can do. But it does give a good enough understanding right here. So I'm going to put in about 40 slices. Okay, so there we go. These are the slices that we're talking about. So now in straight view, if we're looking straight down at the flat region, these are the stripes I'm talking about right here. See, and the stripes are parallel. Okay, and the stripes are parallel. And so later on, I'm gonna even get even more clear about how we put the stripe. But in this way, the machine is putting the stripes completely vertical, completely perpendicular with one axis here, and we don't even have to worry about what axis this is. This could be x-axis, it could be the u-axis, the y-axis, whatever. But all of these stripes are perpendicular to some axis, and I haven't even talked about the axis, so don't be too worried about the axis. But generally, I want you to see, whoever viewing this video, I want you to see that these are parallel stripes. And then on top of each of those stripes here, we erected up those triangles, okay? Those equilateral triangles. So let me reduce the amount of stripes right here so that we can see, have a better view. All right, so now once again, these are the stripes, and we're having less stripes now because I just adjust the setting a little bit and then change that to a less stripes, and then you can see that the stripe length stays variable. The stripe length is quite variable at on some end, right? On each end here, the stripe length gets pretty short, and it can keep getting shorter. But then at some point here, then the length gets to the biggest. But then in the end, on each stripe here, we erect up an equilateral triangle. Okay. And so how do I even know that it's an equilateral triangle? Because looking from a 3D point of view, it's a little hard to see. So now the program I'm using here is powerful enough that I can turn my 3D view around right here. So right here, if we're looking straight at it, okay, it's an equilateral triangle. Okay, so each stripe right there is an equilateral triangle. All right, but then in the end, so think about it cumulatively. Cumulatively, I'm starting to use that term here. Cumulatively, if we reach to an amount of infinite number of stripes in between. So even my software has a limitation, but let me keep increasing. Okay, so now I'm going to increase to a lot more stripes than how we've had earlier. So now the picture becomes finer and finer. Okay, and we eventually form what we see now in front of our eyes. In front of our eyes is no longer just a flat base region. So the base region is still here, but now encountered together with all of these shapes that erected vertically from the base area, that we have a solid, and then this solid has a volume. And that's the whole idea about we want to calculate the volume of those shapes, the volume of those solids. But we're calculating those volumes by slicing them, by thinking of those as they're those volumes come out from the accumulation of slices. Okay, from the accumulation of slices. So just like that. So think about it. What if my base area here was a rectangular setting like this, a nice straight rectangular setting? Okay, so let me prepare my computer view, my computer screen a little bit again. All right, so here's a rectangular region right here. Okay, and again, the machine is using the stripe. The machine is using stripes that are parallel and vertical to this axis here. But at this point, no one really need to worry about what those axes are all about. Okay, but the picture we have, the base region is here. Okay, and then shading those base region, again, just like how I was describing earlier, we're using stripe. Okay, we're using these stripes. So putting these stripes in, it gives us a sense, a visual sense about the region is being shaded. But now think about on top of that, we're gonna put an equilateral triangle, and this becomes the shape that we're looking at. So these are all the slices that I was talking about, and that was in what our discussion title is all about. Okay, each slice here is an equilateral triangle, and in this case, since it's just the way how the picture is, it's just the way how our base area is. Base area has the stripes are being the way how the stripes being placed. In the way how the stripes are placed with the computer, then the stripes are being placed parallel, of course, but perpendicular with the longer edge right here. And so that means in the way how rectangle has to be, then these stripes remain equal length, constant length throughout the whole region. Unlike this area. So there's no hard rule. It all depends on what base area you're looking at. And then so some base area, your stripes, the stripe length remains the same throughout the entire accumulation. Whereas in some other base area, the stripe length goes changing, okay, goes variable depending on where you put your stripe. So in that way, now once again in 3D view, and this is what I'm trying to do right here with my best capability, okay, then we're erecting those equilateral triangle, okay, and that's why we have like a prism shape right there. Okay, the shape that's like a prism, a triangular, an equilateral triangular prism. Okay, that's what we have. So here we ended up with a prism. So prism is one of the very common solid out there that we see every day in our daily life right there. But now we all of a sudden we realize prism can be constructed from accumulating slices. Okay, accumulating slices, and then in respect to or relative to a base area. Okay, so that's a prism. And so this picture here is some solid again, and the volume of that solid is created by accumulating slices. Okay, but in the end it's a little bit not as regular as this one, so we don't even have a name for that. Okay, so that's the idea of calculating volume by slices. Okay, and so I will even talk about why are these so important, and I talked a little bit about how you see these picture in your life. Think about it. You will see some. Think about this shape here. I have randomly driven by those area where it has those house roofs that has this special construction right there. That the base of the roof is in an oval shape. And then they are created by, and once you have that oval shape right here, then the engineer who built that house designed these slices to be equilateral triangle, or just some sort of isosceles triangle erected vertically up from the base area of that roof right there. And there they had a very creative art form roof, okay, with some special purpose. But I have seen roofs like that. You see what I'm saying now? So the point now is that you see these shapes all over in your daily life. I see that in the roofs. You may see that somewhere else out there. Okay, but now let's get real. Let's get into the journey of how we can actually apply calculus into calculating volume of a shape like this, of a volume of a solid like that, or of a solid like this. Okay, so let me now put away the pictures here I drew on the board. So now, before we get far with this kind of problem, allow me to show you the real fundamental. Again, just there's always a fundamental. And I started saying that quite a few times already. The idea now is that we're accumulating those slices. Okay? So, just like that, just like the picture I brought up on the computer screen earlier. So these are our ovals here, and in some 3D view that I'm trying in my best ability to make the sketch. But so these are the parallel stripes right there. Okay? These are the parallel stripes. They're all parallel stripes. And then now we're erecting, all right, equilateral triangles on that. And that's how we are creating the slices. Okay? But now I have to push your understanding even further. Each slice right here has a thickness. Each slice itself has a thickness. Okay? And let me get back to that picture on the computer screen earlier. All right, so here we go with that in this picture. Here's what I'm seeing. Each slice has a thickness. Okay, see the thickness right here, and with a very thin thickness right here, we can still fit more stripes in between here. We can even fit more slices in between each one of these discrete slides right here. So this is only it's sort of like a discrete version of that. Okay. But the idea now is that I would like to enforce. Each slice here, from where it stands, each slice has a thickness. And then from that, each slice created a shape that's erected vertically up in what I said earlier. So at each slice we erected that regular shape right there. And when I say regular shape, I mean it's the same shape, but being placed at different slides like that. So hopefully everybody get clear with that idea at this point. And so that's why the scale of that shape gets large or gets small, depending on where the stripe is at. And so in that case, now I'm talking about the scale of the shape gets large or gets small. I'm talking about the face, the cross section, the area of each erected slice right here. It has an area, okay? And so allow me to, so now we're talking about slice, or sometimes we also can refer to that as cross section, okay? But I'm talking about the space that's filling in here, all right? So each slice has a slice or cross section, area. And that area will also get big or get small, because I was talking about the scale, right? So but the scale is just something in general you can see, but as the scale, as the shape gets scaled up or scaled down right here, the area gets larger or gets small, depending on where we put that shape right there, that slice. Right there. Okay, so we have cross sections area and we have thickness. Perfect. That's enough for the volume of one slice. So all we do is, allow me to use a shorthand writing. So slice area, or alternatively you can call it cross sections area. Okay, multiply with thickness. That gives you the volume of one slice. Okay, and so now how can we see the application of calculus here? So anyone at this point, when anyone arrived to this lesson with me here, you must have seen me, you must have heard me using this word quite often enough throughout other video lessons. An integral that we learn in Calculus 2 is accumulation. An integral in Calculus 2 is accumulation, especially a definite integral. And so how do I apply a definite integral here to calculate this volume? And it makes sense that way, that in order to achieve that area, that volume, in order to achieve that volume, we have to accumulate. This is without this symbol right here, this is only the volume of one slice, but we're not only having one slice, we're having infinitely many slices. As we can fit in infinitely many stripes, many parallel stripes throughout the whole region to fill up that region. And on each instance of the stripe right there, we can erect a shape. So now I still use a shape of the equilateral triangle, but it can be other shapes there as well. Okay, but now, so that's why it gives us a slice area and a volume, and a thickness. So multiplying those, that only gives us the volume of one slice. But now we're accumulating this symbol. Anyone studying with me, I really try my best to put this into your understanding. An integral is accumulation, and I want to put this symbol into your mind as accumulation symbol. Okay, we're accumulating all of those volume, slice volumes from a start to an end. And that's how we're doing it. That's how we can obtain the volume. And that's the general philosophy of these problems. Okay, that's the general fundamental, the most general fundamental, because from here we can do so many various different things with this. And there's no special formula anymore with this. There's only one general understanding here, then general fundamental understanding. Okay, and so now we're gonna keep it, that idea right here. If you have to, go ahead and put this in a box right there, because this fundamental is quite important. Okay, it's quite important. All right, so now I need more board space, and I still want to retain the picture here. And so now allow me to do the following. Okay, so let me erase this fundamental that I'm putting in a box, because I've taught this for years, so it stays with me already. But for you, before I erase it, maybe you can quickly pause the video and note that down right there. Okay, but now once you resume, after noting down this formula right here, allow me to erase that, because I'm showing this fundamental. It comes straight out from the way how I see the picture. Okay, so again, I highly recommend that anyone doing these problems start pushing up your ability to view pictures. Okay, especially to view 3D pictures. Okay, and so now, thickness from that fundamental understanding that we need to identify thickness. Okay, of any slice at any instance and the area. So now here's the idea. In that way, to actually get into, to prepare ourselves for the actual calculation. A shape, a solid is just a solid, a physical shape on its own. There's no axes, there's no x-axis or whatsoever. But because of the calculation need, I'm approaching this slightly different with the majority of instructors out there providing this. But I want students to see this as just any solid on its own. Naturally, it's just a physical shape you're seeing in front of you. And then for the calculation need, we're gonna put on the axes. So think about it. This shape right here, these are ultimately these are the stripes that are parallel. And so now we take advantage of the characteristics of these parallel stripes right here. We're gonna start putting in the axes. So now I'm doing a little bit of a weird look of the axes, but I mean these are in the 3D view right there. So it could be we have our choice actually to just simply, as a matter of fact, when you get advanced, when you are fluent enough, you don't even need this vertical axis. So this vertical axis is just simply to indicate that the stripes are parallel with that vertical axis. But what's more important is this axis where all of the stripes here are perpendicular to. The stripes itself, those stripes themselves through the region are parallel. But then we purposely put an axis, we put an axis that's perpendicular to all of these stripes here. You can call that the x-axis, you can call that the y-axis, you can call it the u-axis, the z-axis, the t-axis. The name on this axis is your choice. And once you name this axis, the other axis is also pretty much your choice. Okay, pretty much your choice. And so, let's not be too wild in that way. So I'll just stick with the traditional convention right here. My horizontal axis here is the x, and vertical axis is the y. Okay, so I'm trying to stay with the usual thing, but I also start pushing your creativity, I want to start pushing your maturity into a little bit of a higher level right there. Okay, in terms of seeing these pictures. And so I just want you to, yes, we stay here with the x-axis, but I just want you to realize and put that somewhere in a corner of your mind that naming this axis is not important. You can name that whatever. Okay, you can really name that whatever. Okay, And so in that way, here's the impact of putting in just, and as I said already, this axis that's perpendicular to all stripes in your region is the one that's more important, because now in the way I'm seeing it, then the stripe here, once you relate that, once you make those slides relative, and remember the idea is that the stripe is not really going through to hit to the axis, but in the end it's parallel, so this area here, this part here should be dotted, okay? But in the end, once we have put on an axis, then each stripe here, the thickness on each stripe becomes a dx or d whatever name you gave for this. So here's the impact. I want to stay with x to keep things standard, but like I said earlier, in what I said earlier, you can name this axis because the name for that axis is not too important. You can call this the t-axis. Then your d expression, then your thickness on each stripe, the thickness on each stripe is now a dt. If you name it that way, that's a consequence. All right, think about it. If you call this the u-axis, then your thickness there, instead of dx, you call it du. Okay, that's a consequence. That's why if we call it u arrow du, that means consequently it's the change, the thickness here has to be the infinitesimally small change in u variable. If this axis here is named or labeled as a t-axis, then that has to be a dt. Okay, and so it might be a little strange for anyone getting exposed to this, but you can also name this axis the y-axis. It's just, like I said, this picture here, I only want you to see that as a physical solid, a physical structure in front of you. So where you put the shape, where you put the axis, that's your choice right there. Okay, and so if you call this axis the y-axis, then of course this thickness here has to be a dy. But these are all. So what do I try to address right here? Once we put the axis on, and we have a way to calculate our, so any of these is just different way to express thickness. All right. So we have a way to express thickness. That's what it is. Okay. And so now here's even a further impact right here. So these are things that I'm writing, in red ink. These things I'm writing in red ink, that's just for you to understand, to have a broader understanding. But in the end, let's get back, now as you already had hopefully a clear enough understanding, let's get back to just the traditional convention by using x for the axis here. Okay, so if we name that x, then the thickness has to be dx. And so think about another impact. The picture, the shape that we are erecting right on top, vertically right above our stripe right here. And so each stripe, and by the way, so each stripe, if we call this axis the x-axis, then each stripe stands right at an x value. That's how it is. Each stripe stands right at an x value as a value x on this axis. And I call it x value because I named this axis the x-axis. If I call this the u-axis, then each stripe stands at a u value. Okay, if I name this a y-axis, then each stripe here stands right at a y value. Okay, that's the impact. And so the further consequence here is that each slice, now look at the area of each slice. So now I just made it clear to everybody that each slice, each stripe here stands at an x value. If we call this axis here the x-axis, then so consequently there will be way. I'm not saying that, I'm not giving you an answer right now, because each shape has a different way, okay? Each shape has a different way to determine, but there will be way to determine the area of slice, okay? Each shape here, each slice here can be the area on each slice. That's what I meant. Okay, can be expressed. That allow me to use equal sign. The area of each slice can be expressed as a function in terms of x. That's the critical part to understand right there as well. Okay, that's the critical part to understand. So we name this name of the axis. We have our own choice of naming it. Okay, and then so now as an impact, the thickness of each stripe consequently became the thickness of each slice right here is the dx, consistent with the name we gave on that axis right here. And then of course the stripe is right at the x value, okay, consistent with the name. If we name this the t axis, and each stripe is at the t value, okay, and this thickness here is a dt. And then since I'm using x here, then the area on each slice, the area on the cross section of each slice can be expressed as, that's what equal sign is for, can be expressed as a function of x. That's what I pointed at the arrow to. All right, and so now in that fundamental that I pointed out earlier, yes, volume for one stripe, volume for one slice is always can always be found by slice area multiplied with thickness. And I'm coming back to that same fundamental, and then from a start to an end right there. Okay, from a start to an end. And then now, but now after I gave this hopefully detailed explanation enough, then think about it. If we call this axis here, if we reference this picture in reference to the axis that we name x, then the thickness becomes a dx. That's just what it is. Slice area can be expressed as some function in terms of x, and I set this as a promise earlier, and I have to confirm again. I have to assure you there will be way. It's just we haven't found anything for this one yet, but there will be way. There will be way for us to express the slice area as a function of x. So that is the volume of one slice, and now we're going to be accumulating. That's what the formula, that's what this general fundamental formulation becomes. Okay, and then think about it. Once we put the axes on, then the starting of the accumulation starts here, wherever some a value on this axis to some b value on that axis. That's where our region, our base region starts, and this is where our base region ends. And so the accumulation takes place from A at start and ending at B. This is a little bit more of a particular version, and I believe I have seen many textbooks, many standard calculus textbooks deliver this formula right here. Okay, but again, you see, I want my students to understand this fundamental instead of being too worried about formulas. Because so, hey, what's the impact here? If we put this axis here, if we name this axis the y-axis, then this is the integral from a of y times dy. If we name this axis right here the t-axis, then this integral is the integral from a to b of a of t dt. Okay, and so this formula can change quickly, but the only one fundamental formulation remains exactly the same. All right, so surprisingly, that's all the fundamental theory I need to point out. Let's get to really doing some problem right there. Let's get to really doing some problem, and you will have a better hang of what's going on right there. All right. So in that way, allow me to quickly erase the board to make some space for myself, and then we're gonna start getting into that. All right, so let's now call that our example 1, okay? Because since I delivered this example right in this general lecture, then this is our first example in this particular general discussion lecture right here. So in this example 1 right here, let's look at the wording description of our problem. The problem is asking us to find the volume of an object or a solid, right? That described as follows. So the base is the region. The base is the region bounded between y equals x squared plus 2. So there's one curve, and y equals x. From x equals 0 to x equals 4. Okay, so this is the description about the base. So at this point right here, connecting back to the general discussion I've had before we started into doing examples here, then pretty much everything we're doing about the slice method right here it has to start out with knowing the description of the base. So it's always the first thing to know. And that's exactly what's showing in the wording of the problem. So the wording of this particular example here is a very standard wording of these kind of problems. We first have to understand the description of the base region. Okay, so that's what description number 1 is all about. So the base is the region that's bounded between, there are the two curves here, and from x equals 0 to x equals 4. Okay, and then once we have a clear understanding of the region, then we're going to look at the description of the cross section. So the problem here uses the wording cross sections, but in other words, to make it consistent with what I was saying, with what I was teaching earlier, and I did use this term as well, but cross section is equivalent to the slice. So any cross section is a slice, just as a clarification like that. Okay, but let's get to that later. So for now, let's try to understand our base region. So we have two curves, and the base region is the area that's bounded between these two curves from x equals 0 to x equals 4. All right, so now I'm going to turn over to my favorite graphing device right here with decimals. Okay, so now x squared plus 2 is this graph. Okay, that's x squared plus 2. And let me put it in a good level of zoom right here. So that's x squared plus 2, and we don't really need to see the numbers on the graph right here, so allow me to hide all of those in numbers. And so y equals x is this line, is this graph right here. So y equals x squared plus 2, y equals the x. So now we see we have these equations, we have these two graphs right here. Okay, and now between x equals 0 and x equals 4, from x equals 0 and x equals 4. So x equals 0 is right here on the y-axis, and x equals 4 is right here, okay, crossing through the vertical with the x-axis. So now it looks like I have to zoom out a little bit, okay, but the enclosed region has to be the region right in here, not here, not up here, not anywhere else, only inside of this. So now really let me put it in the shading right here to make it real clear. So there is our picture over here. That's our picture, okay, of the base region. All right, and so now upon having a good look at the base region, let's now read further. Let's now look further into the wording description of our example to find out what the requirement of each cross section is. Okay, because think about it, we can put the stripes, see, these are the parallel stripes. I'm trying to use my mouse motion to put parallel stripes like that. It works too, okay, but that's just not the description of the problem. That's not what the problem is asking us. That's not how the problem is asking us to put the stripes, okay. We can also do the stripe like this, horizontal. That's if we are making our own problem, okay, we can put stripes like this. Okay, but that's not how the problem describes the slices. So now we have to stay with the description of the slice. So now every cross section perpendicular to the x-axis. This is the important the description right here. So the cross section I already explained earlier, that is nothing but just the slice. So each slice or every slice, right? Every slice perpendicular to the x-axis is a square. Okay, this is another piece of important information. Every slice that's perpendicular to the x-axis. So right here, just extract immediately the understanding about perpendicular to the x-axis. That means on our picture, on our graph right here, we have to place the stripes. We have to put the stripes. This is the x-axis. Okay, so the problem also, even though when I was giving the general discussion, I was making it to look like, and as a matter of fact, it is under our control, but here we're doing a problem that has thing already described for us, so we just go with that description. But so the stripes here are parallel, the stripes here are all perpendicular to the x-axis. And see, think about it, consequently, if all stripes are parallel, are perpendicular with the x-axis here, then they have to be all parallel with each other. And so once again, it comes back and agrees with my explanation earlier that all the stripes have to be parallel. Okay, And so in this case, if we have the axis going this way, then the stripes are all perpendicular, because that's the way how Euclidean geometry is. For segments that are parallel, then once we put on a line that's perpendicular to one of those segments, it has to be perpendicular to the rest of them. Okay, and so now back on that picture, that's the shape of the region, that's the shading of the region, and the slice, once again, the slices are expected to be this way, perpendicular to the axis. Okay, and so now on this shape now, allow me to put in the stripe here so that I can start animating the stripe. So earlier we didn't have the stripe, and now I put in the stripe. So now let me adjust the stripe here so that we can see how the stripe length changes at different various values. See, so now when we're somewhere closer to the beginning, right, then we have some length of the stripe, and the stripe here is the black little segment right here that connecting between the upper curve and the lower curve right here. So now you can observe and see that the stripe length gets longer, or basically gets changed as we change that to different x value. And so just consistent with what I was explaining earlier, every stripe, once we call that axis, once we call this axis the x-axis here, then every stripe is at an x value. Every stripe is at an x value. And so in that way, now we can see that the length of the stripe changes depending on where on the x-axis that we put that the stripe is currently at. Okay, so that's another thing to imagine. All right, and so now we are ready to switch over to 3D view right here. Okay, so here's my 3D view right here. All right. So now that's the region that we are shading. This is the region, and this is the what's so-called the x-axis earlier according to Desmos. And here I have to switch to a different program. And so once again, don't even have to worry about these f of x or g of x or whatsoever that is. Right? But this is the curve, and this is from x equals 0 to x equals 4 here. And this is the curve x squared plus 2, and this is this is y equals x right here. Okay, and so now I'm going to increase the number of stripes in 3D view. So I already placed a stripe right at x equals 0. So now let me show everybody. So there's a stripe. And so the length of the stripe, according to the way how it is right now, the length of the stripe is whatever. We will learn to calculate that. Okay, but in this way of calculating the length in each way right here, then at each stripe, now I'm going to put in more stripe. All right, so now at each stripe, if we place a square, so here's the cross section that looks like that's what the square on each slice look like. Okay, and then now in that way, let me even increase to more stripes here so that you can see a finer shape, a finer picture over here of that. Okay. All right, so now here's our solid. That's the solid that we're looking at in a really nice view that my computer software, my computer animation is doing that for me. Okay, and so right, so that's the picture of the shape right there. All right. So now it's really hard to see the distance between each stripe right there. Okay, and I'm trying to put in different angle view right there for everybody to have a look at. All right, so now let's get to really do the calculation of that volume right here. So now on my board, I only need to construct that flat figure. So the idea now is that, and when I'm going over that, I want to stay, even though the problem gave us, y equals x squared plus 2, and then the y equals x, right? But I want you to focus that generally the shape the shape in the beginning picture of the base, the shape of the base region looks as the following. After we have put in all the 4 boundaries right here, then we have the following shape. Okay, so we have that shape, and we have, and forgive me if I'm upscale or anything like that, but that's what it is. So the axis, and I don't even need the other vertical axis. I only need one axis, this axis here. Let's call that the x-axis. Let's call that the x-axis. And so now it starts at 0. It ends at, this is 4. Okay, so each slice is a square that's being constructed, being erected right above this. Okay, and as you have seen that in the picture. And so, but any stripe here is perpendicular to the x-axis and stays at some x value between 0 and 4. And that's the idea right there with that. Okay, and so now in that way, just like how I was explaining, so what we need is to look back at that fundamental. We need to find a way to formulate the slice area. Okay, the area of one slice. And then we multiply that with thickness. And then that product here gives us the volume of one thin slice. And now I'm going to be accumulating all of those from a start to an end. That's how I get the volume of the total picture of that total solid that we've seen earlier, that overall solid. Okay, so in that way, here's how I see it. My personal favorite, it's just my personal experience. I start out with identifying the thickness here, but really it shouldn't matter too much actually. So thickness in the way how I explained earlier, before we stepped into any of the example, then thickness here in the way how I place my stripe, then thickness, and in the way how I name my axis and how I place my stripes, those two informations together, thickness has to be dx, because I name my axis here the x-axis. Okay, and this is not really I name. The problem actually named for us. All we do is just we try to realize and recognize it from the problem's description. Okay, so thickness here has to be dx, consequently. And so in that way, now we got thickness. Let's step over to step 2. But so let's do this. As we found some information, let's start revising our fundamental with the new information that we have found filled in. So this integral, this accumulation, it's accumulation from start to end. Slice area, we haven't found it yet. Let's leave it here the way it is. Slice area or cross-section area. Some textbooks call that cross-section area. Quite a few actually. Okay, and then the thickness here is now known as the dx expression. So now at this point, if we're connecting this with that same fundamental how I have always been teaching my students, once we see this d expression in our integral problem, then we're expecting that this area that's coming next has to be expressed in terms of x, because that's what expressed here. Okay, and so that's how you can see things being all connected and consistent together. Okay, and so now thickness is dx, and so in the way how we place our stripe, remember the square on this stripe comes out this way, and the thing with the square, if we're looking straight at the square, if we're looking right at the square like that, if we're looking right at the square, then the square has 4 equal edges. Okay, if we're looking right at it. So, or how about let's not squeeze in the space here. Let me quickly navigate to the other board and do that quick scratch work there. Okay, the square has 4 equal edges, and then so if this is the base right here, then that base is having length x, because that base here is the same as this edge right here in our picture. So this is and that edge right here, whatever length that is, then this is the same length, this is the same length, and this is the same length. Okay, and so, and that length there in this picture, that length there in this picture is the difference between upper curve and the lower curve here, and we will be able to find that out. Okay, we will be able to find that out. And so let's get to it. But then in the end, we can kind of sketch out a plan ahead. The area of any square, area on any square on any slice here has to be length times length, or just L squared. Okay, something to kind of know ahead a little bit. Okay, so let's get back to the other problem right here. And now I see I have to put in some labeling here, but this line right from the beginning was expressed as a function of x, y equals x. And that's probably the reason why the computer software that I was using always tried to put things in terms of the two functions f of x and g of x, right? The upper curve and lower curve, but that's not really the important point. Okay, all right, and then it's kind of misplaced anyway, so let's not rely too much on those notation there. But so the lower curve that determines the lower curve that limits my length of the stripe is this line right here, y equals x, or you can think of that as some function, you know, maybe h of x or g of x equals x. This upper curve right here is what limits the height of our stripe right there. Okay, the upper limits of our stripe, which is the line y equals x squared plus 2. X squared plus 2. So in that way, it is apparently clear. And the good thing is the problem that we have here right at start gives us the expression of each curve here, each boundary here in terms of x already. Okay, and even the starting point here is a vertical line, the ending point here is a vertical line perpendicular with the x-axis. So we start at this x, and we end at that x equals 4. We start at that x equals 0. And that we'll explain a little bit more later. But now it looks like the length here has to be obtained by the length on each stripe here is obtained by upper curve. Okay, subtract lower curve. And in that way, I'm looking at x squared plus 2. That's the upper curve already expressed in terms of x minus the lower curve x. And now all of a sudden I formulated for myself an expression in terms of x right here. Okay, that's the length of each stripe. Okay, so this is the length of each stripe. But as I said earlier, area on any slice being a square, in this case, in this problem, area on each slice is the area of a square. And so area has to equal the length square. Okay, length square. But this is our length right here. This is our length. Length is expressed as a function of x squared plus 2 minus x. Okay, or for short, we can just write that as as a simplified version. Okay, as a reduced version, we can write it as x squared minus x plus 2. So that's the formula that determines the length of our stripe anywhere we place our stripe on this axis that we named x. Okay, and so now here we are so ready for the slice area, slice or cross section. Okay, area. So the slice area has to be the following: square of the length. That means it's gonna be x squared minus x plus 2, but all square. Okay, x squared minus x plus 2, all square. So all of a sudden we realize slice area, just like that quick little formula I explained earlier. We got dx, and then this area of the slice of this each slice here just now was expressed in terms of as a function of x. So back to what I said earlier, it was never a line. There will be a way to figure out the expression of the slice area in terms of the variable on this axis, whatever that axis is that we name it. Okay, so that's the idea of the problem. So now we are so ready to put all this together. So slice area now can be substituted by this expression right here, x squared minus x plus 2 all squared. I'm going to fill it in. X squared minus x plus 2. okay, but r squared, and multiply with thickness, dx. So ladies and gentlemen, this is the formula that calculates volume of one slice right here, volume of one slice. And now once we have had that, now it's time to accumulate all slice volumes from the beginning to end. So the picture is making it clear. The beginning slice, the first slice, the beginning slice have to happen right at x equals 0, because we're standing up a square right here. Okay, you can imagine that there's this piece of paper, being a square, okay, and we put it right here. All right, and then it's accumulating up. And so in that way, it starts at 0, the accumulation starts at x equals 0 and ends at x equals 4. So now we have completed our volume, our integral setup for this volume, 0 to 4. That's how we completed our integral setup for this. Okay, and so now once we have had the integral setup, the rest of the work is easier. And that's why I said earlier in the beginning of this lecture right here, we must learn this video lesson after you have learned about what the definite integral is, definitely. And we also must learn this lesson here after you have learned about what the fundamental theorem of calculus is, because that's the tool I'm going to use to evaluate this. Okay, so in order to come up with the final answer for this integral, I am going to use the fundamental theorem of calculus. Okay. All right, and so now allow me to spend some time rewriting that complete integral setup from the beginning. 0 to 4, x squared minus x plus 2 r squared dx. Okay, and then with an integral like this, first step is to use some algebra to FOIL out this square over here. Okay, so that will give me an integral from 0 to 4 x to the 4th minus 2x cubed plus 5x squared minus 4x plus 4 dx. So let me rewrite this into a little bit of a better space right here. Make the spacing a little better for myself. 4th minus 2x cubed plus 5x squared minus 4x plus 4. All right, and that's multiplied with thickness, dx. So all of this here, you can double check me by FOILing out x squared minus x plus 2 times x squared minus x plus 2. By simply FOILing out that and simplify properly, we should be arriving at this. But all of this here in the end is the area of each slice. Okay, the area of the cross section on each slice right there. Okay, and so now once we arrive here, then the integral is really ready for us. So fundamental theorem of calculus says we need to first find the antiderivative. So 1/5 x to the 5th minus 1/2 x to the 4th plus, and then 5/3 x cubed minus 2x squared plus 4x. Okay, and now with this, we're gonna evaluate that according to the fundamental theorem from 0 to 4. So the calculation will eventually get a little lengthy. So after setting down the calculation, writing down the calculation setup, I'm gonna step over to my calculation desk. My calculator on the computer station right there to have the value calculated. But here we're looking at 1/5 4 to the 5th minus 1/2 4 to the 4th plus 5/3 4 cubed minus 2 times 4 squared plus 4 times 4. Okay, and then that is the antiderivative at 4 at the upper limit right here. And then think about it, if we substitute a 0 into the entire antiderivative, we're looking at just all a 0 out right there. And so what matters for us here is just to calculate this quantity right here in that. Okay, so I'm going to quickly step away back to my computer station and grab a computed value. All right, so my answer came out being 2512 over 15 right here, and that is the volume of this solid right here. Okay, and that's how we're done our first example right here in this particular problem right there. Okay. All right, and so here we are ready for heading in example 2 right there. All right, so let's now turn over to the wording description of the problem on the computer screen here. And so, all right, so here we are. The description say, so in example 2, the description says we want to find the volume of an object or a solid described as follows. So just like how I explained back in example 1, then anytime we are doing calculating the volume of a solid by performing the slicing, by accumulating slices, the volume of slices, then there are always two key characteristics. First, there has to be a description of the region, of the base region, which is what it is right here. So the description number 1 is here. The base region is bounded by two curves in this case. So y equals x squared plus 1, and the other curve is y equals minus x squared plus 2x plus 5. And so at this point, we're not going to be too worried about whether we're going to have to rewrite these expressions, or is this a function of x or a function of y. That's not what we need to worry right now at this point. So just right now, we have one curve being represented as the equation y equals x squared plus 1, and then the other equation is y equals minus x squared plus 2x plus 5. And then once we have a clear understanding with the description of the base region, then we move on to understanding the description of the stripe right here. And so I will get back to that. But so now let's switch over to the graphing space on Desmos right here, on the graphing calculator on Desmos, to see what the base region looks like. All right, so on my blank graphing space here with Desmos, I purposely did put these graphs here out of order. So the two curves, and allow me not to explain which one is which. Allow me not to mention which one is the graph for x squared plus 1, which one is the graph for minus x squared plus 2x plus 5. So allow me not to distinguish between the two, because I want to also go over that skill again in this lesson, even though we might have seen that skill before in algebra. Okay, but so here this is just basically the two graphs we have. One of them looks to be and this time right here the two graphs crosses. And unlike example 1, we don't have a starting end and an ending end, so we are responsible to find the starting of our region, our accumulating region, and the ending of our accumulating region, which apparently looks like it's these 2 points right here. But we will also have to find those 2 points later. Okay, so now the enclosed region, or the region bounded by the two curves here, has to be the region inside where I place my mouse cursor right here. It cannot be out here, neither that one, and neither any of these. Okay, so now allow me to put in the shading. And yes, the shading describes it all. So from where the y-axis here, okay, then we can see that all right, and so now once we are done looking at the enclosed region of the base, then now let's look at the description of the stripe. So every cross section, or just like in the term that I delivered in the general discussion lecture, in the general discussion earlier, then a cross section is a slice, and so every cross section that's perpendicular to the x-axis. All right, so the cross section is perpendicular to the x-axis, and in my explanation that I've had earlier in the general discussion, before we get into the examples, then any of those cross section or slides came out from the stripes that we shading through the region. So in this way right here, let me get back on Desmos, and we're gonna find out, we're gonna have a look at the stripe based on the description. So the stripe, all the stripes are perpendicular to the x-axis. So this is the x-axis. And so now my stripe has to be as following. So these are the stripes right here. So now the stripes, and anywhere I place the stripe, so the stripe is perpendicular to the x-axis as described, and then it looks like the stripe and all of our stripes change the length right here as we look to different stripes right there. Okay, so now that's enough the description of our solid right there. And so now think about it. The description now says a little further that so the cross section that's perpendicular to the x-axis is a semicircle. All right, so that means think about back on this graph right here, then right over the stripe, right over any stripe, we're gonna erect a circular or a semicircle shape right above that. Okay, so now in this way, allow me to swing over to the graphing my other graphing calculator so that we can see the slices easier. All right, so this is the description in 3D of our base region right there. And so and still I have not decided which one is the upper curve and which function is the lower curve. Let's leave that for later. And then it has a start here and it has an end here, which is the crossing points, which are the crossing points of the two curves here. But we will also get into finding those. Okay, but right now in the way how it looks, here's the region right here, the base region. So now let me put in the stripes right here. All right, so that's the way how it looks at some stripe. Okay, that's the way how it looks. We have a semicircle erected on right over that. And so now let me really increase the number of stripes, the number of slices or cross sections. All right, so now I increase to a good number of stripes so that we can, or cross sections, so that we can start recognizing the shape right here. So let me kind of turn that around so that we can have different views right here. So this is the view where we can see all the slices. Okay, and now this is in a different rotated view right there. Okay, and that's the shape, and whatever name that is, I don't even know what that name is called. Okay, but that's going to be the solid that we are about to calculate the volume of this. All right, so now enough with looking at picture. I'm going to make a sketch here on the board, and then we're going to start breaking down the information one by one right there. All right, so in the end, after I show the picture, in the end, what I see here is that we have a region that looks kind of like that. Okay, and then we put an axis on, and the idea, just like how I explained in the general discussion, then mainly because our stripes are described to be perpendicular with the x-axis. Okay, and that's why the axis here being the x-axis really pretty much is just a name. And so having the vertical axis here is not that important, but I'll just put it there in case anyone feeling a little shocked. And indeed, I actually noticed that I put it at the vertical. If I put it there, I put it at the wrong place right there. So it should have been this vertical line right here to be the y-axis. Okay, but so any stripe is perpendicular with the y-axis. I mean parallel to the y-axis and perpendicular to the x-axis. Okay, and then it's our responsibility to later on find out where the two crossing point of the curves are here. Okay, so one curve goes this way, the other curve goes the other way. Okay, and that's why we have the region in between. Okay, and so now again, that fundamental I introduced in the problem. What we need here, and so the semicircle, here's our stripe perpendicular to the x-axis, so the semicircle is erected right above that like this, and just like you have seen that in the picture. So now, again, let me repeat that fundamental. All we need now is that we need to figure out a way to get our slice area, or the area of one slice. The slice area, and then we're going to multiply that with thickness. If we look directly at each stripe here, each stripe itself already has a thickness. Okay, and so once we erect that shape over the stripe right here, then we're going to be able to obtain a slices area and then we multiply it with the thickness. That gives us the volume of one thin slice. And then just in that fundamental about accumulating about an integral, a definite integral, we are accumulating all of those stripes, all of those slices, volumes, all the way from a start to an end. All right, and now a little further before we really get into the problem, and you can see that each stripe here, or the length of each stripe is limited, okay, or is determined by the boundary that's created by the two curves. Here there's an upper curve and there's a lower curve, and at some point throughout our progress, we will be able to find out who's above and who's below over here. In this problem, I purposely did not mention who's the curve above, who's the curve below, so that I want to remind viewers and students of mine how that vital skill, how to decide in case your graphing calculator just simply throw you the graph without labeling, okay? And so I will hold on to the labeling right there. Okay, so now here's that fundamental idea about getting that volume. And so now thickness, just like in example 1 that I did, thickness is always, in my personal choice, like that, it's always what I start out first. So I'm going to look at this picture, and I see that in a way how each stripe is being placed perpendicular to the axis here. And like I said in the beginning of this general lecture, then I said the name of the axis here is not that important. So whatever we name it, so here the problem already named it for us. So since the problem named that for us, that this is the x-axis, then we can call this the thickness here simply dx. It's just the infinitesimally small change in the x value if we call this axis the x-axis. Okay, so everything I'm moving here is I'm trying to stay as close and as consistent as possible to how I explained that in the general discussion lecture. Okay, and so, or in the general discussion part earlier before we got into any of the examples. And so the thickness here has to be dx. And so now in that way I am going to partially fill that into my curtain, into this formula that reflects our fundamental. So it's accumulation from start to end, okay, and then we still haven't found the slice, the area of the slice, so I will leave it there. All right, and then we multiply that with thickness dx. So now the thickness has an expression for that. And so now in my style of approaching definite integral, then once I start out identifying the d expression in the integral, then now it gives me a clear direction that in the next step, when I finish finding the slice area, when I finish expressing the slice area as a function, then it has to be a function in terms of x. All right, so let's move on to the next step here. So now it's time to figure out cross-section area or the slice area, okay? The slice area or the area of one slice right there. Okay, so let's find out. And notice, again, I keep reminding, and let me swing back in the picture again. All right, so here in our picture, each slice here, see, at each slice here we have so these are the slices, these are the stripes right here, and on each stripes we erect, okay, we erect a rectangle, a semicircle over that, and that's why the shape looks like these right here. Okay, so these are on different stripes, and then those create different slices right here. All right, and so now being a semicircle for each of the slices right here, and the length of and so it makes perfect sense that the base of the slice right here has to be the diameter on each slice right here, because the diameter of the circular face, but it's only a semicircular face right there. Okay, so now keep that understanding in mind right there. So now we're gonna move to the other board and think about the circle a little bit. So complete circle, here's the diameter, okay, and so the diameter here is going to be twice of the radius. So this small little space here is the radius from the center out to the circle, like there. But the picture we have here is only each slice we have. If we're looking straight at it, right, then it's only a semicircle. So diameter is here. Okay, and this diameter is the length of our stripe wherever we place this slice on top of. Okay, so keep in mind that the diameter here is the length of the stripe. And so now the length of the stripe, the area of any circle is a pi or square. And then for semicircle, it's 1/2 pi or square. That's a plan right there. That's a plan. This is just common understanding. Okay, we don't have to wait until calculus 2 to know the stuff. All right, so that's formula in general for area of a semicircle. Okay, so now, but keep in mind again, our diameter right here is exactly the length of each stripe wherever we place this slice on top of, or we place the slice over. And so now, let's get back to the picture itself right here and figure out a couple other things. So now on each slice here, so we have a semicircle over that, but now let's come up with a way to determine the length of the slice right there. Determine the length of the slice. I mean the length of the stripe right here, because the stripe will become the base, the diameter of the slice, being the semicircle. Okay, and so according to the picture, then the length of any stripe is determined by the difference between upper curve and lower curve. Upper curve and lower curve. Okay, upper curve minus lower curve. So it makes perfect sense by looking at picture. But now we have two functions. One of them is the x squared minus 4, okay, and actually x squared plus 1. That's one of them. And the other one is minus x squared plus 2x plus 5. We need to determine between these at least which one is above the other one in between this interval right here. Okay, that's the challenge right there. That's the challenge. But now in order to, and like what I said earlier, we need to determine who's above and who's below in that interval between the two crossing points. But the big problem, the bigger challenge now is that we haven't found out the two crossing points. We have not found out the two crossing points. All right, so in that way, we are forced to do a little bit, some other things before we can get to calculate the actual length. So the only way to understand where the two crossing points, and the crossing points are measured in terms of the x value. So we need to find out what's that x value here, or what's that other x value here on this axis, so that our graph here is crossing with the other graph. Okay, and so now the standard work for finding intercept of the two graphs is simply just, we're going to set the two graphs equal to each other. I mean the two functions equal to each other. So x squared plus 1 is set equal to minus x squared plus 2x plus 5. Okay? And so in that way, I am going to bring all of these over, all of the terms over to the left-hand side and produce for myself an x squared. And by the way, at this point, we have an equation to solve to find for x value. And so I'm going to bring all terms to one side. That's producing for me 2x squared minus 2x minus 4 equals 0. Okay? And allow me to move a little bit fast pace in terms of moving around these terms like that. And so now clearly we have a quadratic, but before we rush into solving it, there's a common factor of 2 among each term here. So why not canceling it, to reduce our equation a little bit further? So I'm going to cancel both sides by 2. Both sides by 2, so every term here is canceled by a factor of 2. So now it becomes x squared minus x minus 2 in the next step. And now with this equation, we can go ahead and take our own favorite choice or our own favorite methods to solve for that equation for x. And so I will use factoring because it comes more directly for me. But you don't have to go with this method, because I'm assuming anyone watching this lesson is already fluent with how to solve for a quadratic equation, how to solve for x, or how to solve a quadratic equation in general. So here with factoring method, I found out I have x plus 1 times x minus 2 as my two factors. So that means that leads to this equation will give me two solutions. One of them is -1 and the other one is x equals 2, and allow me to skip that detailed explanation about how from here leads to having the two solutions there. And anyone viewing this video should be already fluent with the skill, or you can Google search anywhere, or grab a standard algebra textbook and it has all that explanation here. Okay, but now if we're looking at these two values, so they are from small to large, it's -1 and 2. So that makes perfect sense with the way how the picture looks. Okay, and then I can also swing back to the browser like that. See, in the way how the picture looks, then it looks like this point right here is to the left. This first crossing point is to the left of the y-axis here, and this other crossing point is to the right. So it looks like -1 has to be here and 2 has to be there. All right. So now at least once we have found the two crossing points, and now we know that x equals -1 is here, and it will also be further beneficial for us. So right now we simply found that to serve the purpose that we want to know what interval we're looking at here to decide who's above and who's below inside of that interval. Okay, and that's the plan right now. So now once we know that we're currently, we don't need to worry about anything outside of that interval from -1 to 2, but it's just right in between here and between the two curves now. X squared plus 1 or minus x squared plus 2x plus 5. Who's the bigger and who's the smaller? Okay, because we need to determine who's the upper and who's the lower, so that eventually we can take the difference and calculate our length between as an expression. All right, so in that way, now let me swing over to the other chart, the other board again, and I am quite sure throughout the quarter that you're learning with me. Anyone studying with me at this point, I'm quite sure that you have seen this being used sometimes here and there, even prior to this video lesson already. But in case you haven't seen any of that, then here you have an extra opportunity to review that. But so in between -1 and 2, just in between -1 and 2, all you have to do is just pick a value. Okay, so I'm gonna pick a value to check for. So I'm gonna pick x equals, how about 0? Because x equals 0 is greater than -1 and less than 2. It's a value in between. X equals 0 is the value on the x-axis that's between -1 and 2. Okay, and then and anyone else watching the video can choose a different value as long as the value is between -1 and 2. And then I'm going to substitute that into both functions. One of them is x squared plus 1, which is giving me 0 squared plus 1. The output is 1. The other one is -x squared, which is -0 all squared, plus 2 times x plus 5. The answer here is 5. So now it's apparently clear that this one here, x squared minus x squared plus 2x plus 5, is greater than x squared plus 1. Now, not throughout the entire domain, but at least in this interval between -1 and 2 right there. So that's the way how we can decide. So in that way, now I'm going to get back here and be firm. So now, upper curve has to be that minus x squared plus 2x plus 5. So now we can legally put down the label. So this curve here is the minus x squared plus 2x plus 5. Okay. All right. And this skill, I mean, if anyone is asking yourself or having a curiosity for like, why am I wasting your time showing this? But if you already knew the technique, that's good. You can skip the step I'm doing right here. But I'm worrying for students who are viewing this lesson but still unsure how to determine, and your technology is not doing the job of putting in the labels. Then and you forgot some of your algebra. Then at least there's still a way to decide who's the upper curve among the two given ones, and then who's the lower curve in an interval right here. So this time, this curve right here inside of that interval will become the upper curve. And the other one here gives the bottom one. So the other one, now I have to make a label here for that. Okay, the other one is the x squared plus 1. Okay, x squared plus 1. All right, so now once we're clear with the two curves, who's above and who's below, then again, back to this fundamental. The difference here between upper curve and lower curve is going to give us a general expression for our length at any x value. At any x value, we're going to have the length. Okay, we're going to obtain the length of the stripe by, this is minus x squared plus 2x plus 5, but minus the x squared plus 1. This is the length of any stripe. Okay, but that's not the slice's area yet. Okay, so I'm going to now move on to my other board to sketch down that information. All right, and we are so close. We keep getting closer and closer to derive the general expression for the slice area. Okay, the area on any slice. Okay. So now here's how it works. So again, as a picture of reminder right here, this is the stripe. So this stripe here, now we know it has length minus x squared plus 2x plus 5, right? Minus the x squared plus 1 function. This is all for that length. Okay? But then our picture here, our slice here is a semicircle. So and this is radius. Okay? So area equals 1/2 pi times radius squared. So now we need to, but this is only, this expression here is the entire diameter. And so now I'm going to go ahead and simplify that. Minus x, so all of these here together is a minus 2x squared plus 2x plus 4. Okay, minus 2x squared plus 2x plus 4. And then with that, let me revise it here. Okay, and now I'm going to revise that there. Minus 2x squared plus 2x plus 4. But now that is diameter. So this means the radius is only half. So that means radius is minus 2x squared plus 2x plus 4, but being divided by 2. So now we can see that radius must be minus x squared plus x plus 2. That's the expression for radius. Okay, and so now once we've had radius, then our area formula is ready. Area now is going to be 1/2 times pi, okay, times the radius square, which is now minus x squared plus x plus 2 all squared. Now we have had our final expression for the radius, for the area of any slice at any stripe. So any stripe is being placed, any stripe has a length that depends on the x value on the x-axis where we place the stripe at. And then from the length of the stripe, we are able to derive the general the formula, okay, or the general expression for the area of the slice erected on top of that, over that stripe. And so now that area, so now I can legally write down this area of the slice. So the slice's area is 1/2 times pi, okay, times the minus x squared plus x plus 2 all squared. And this general expression right here in terms of x will be filled in here. And before I'm filling it in, let me remind anyone, we have to double check, is this in terms of x? If we're about to put that in here, this needs to be an expression in terms of x, because this d expression is in terms of x. Okay, so have we satisfied the requirement? Yes, we have. And so now in this case right here, slice's area is going to be so now allow me to write that a little shorter, but it's 1/2. Okay, now minus, and now 1/2 pi times minus x squared plus 2 plus x only actually, plus x plus 2 all squared. And that's our area of the slice. And then all of a sudden we feel like we actually have found our start and the end of the accumulation, because back to this picture, and I have shown the algebra work earlier, the crossing points we had found previously were from -1 to 2, and the accumulation only happens inside of this interval. So it now makes perfect sense that this accumulation, the accumulation of all slices, volumes, we'll start at -1 and end at +2. But ladies and gentlemen, this is the complete integral setup to calculate the volume of our solid. Okay, the solid that was found in here. This is the solid. Okay, so once we finish evaluating the integral on the board, that will be the volume, how big that solid you saw on the computer screen just now. Okay, and so now in order for me to proceed, I have to erase this extra information here. All right, so let's get to it. And so in the next step, I am going to pull out that 1/2 pi because it's a constant coefficient in front of the integral, and at the same time I will also FOIL out that expression here. Okay. All right, and so now what I have here, 1/2 pi times the integral from -1 to 2, and as I said earlier, I will pull out the constant coefficient and FOILing this out. And so allow me to just write down the final simplified FOIL to work, but then you can always double check me. Okay, you can always verify it. But and I will mention that later, but this is x to the 4th minus 2x cubed minus 3x squared plus 4x plus 4. Okay, and all that here multiply with the thickness dx. Okay. All right, and so once again, just as an algebraic reminder right here, but in order to get this FOILed the final expression right here, all you do is think about this square here. In case anyone wonder, think of that square as the minus x squared plus x plus 2 multiply with that exact minus x squared plus x plus 2 and start distributing the terms. Okay, and that's how I arrived at this. Okay, but so now, and you can always pause the video to verify yourself and to verify how I've gotten that. But now once you have completely verified, then the fundamental theorem of calculus now is going to be the main tool to evaluate this definite integral. So I'm looking at so now the next step is to find the antiderivative. So I'm having a 1/2 pi here and multiply with first term gives me as the antiderivative there 1/5 x to the 4th minus 1/2 x to the 4th minus x cubed plus 2x squared plus 4x. Okay, and then I'm going to go ahead and evaluate from -1 to 4. Okay, so it will take some time to write down the substitution work, the work that I'm substituting in the two values here. So I'm going to skip that step right there because anyone viewing this video lesson has seen that often enough. Okay, so I'm going to instead use my computer screen because so that otherwise it's going to take a lot of writing space here. But basically just in the next step we're going to take 4, substitute into each term here, and take the whole -1, substitute into each term of our antiderivative here and subtract the 2. Okay, just like how we have done that so many times. So now I'm going to step over to my computer station and grab a final calculated answer for this. All right, so my final calculation with my computer calculator gave me 81 pi over 20. All right, and that's the final answer. Okay, and so I believe I double checked and triple checked my work throughout example 1 and example 2, but in case I made any silly errors right here, please forgive me, but those are just mainly the slight calculation computational errors right here. It shouldn't impact it shouldn't alter the structure of the problem at all, okay, of any of the problems that we've done throughout the 2 examples. But that's how we found the volume of those solids by creating the slices and accumulating the volumes of the slices. Okay, but so now I said earlier that why is this method useful, and especially why is it useful to be able to see the shape of a solid by by creating slices. Because so I pointed out that a quick example of my own experience, my own personal experience, that there was one day earlier that I drove by a house that has a roof that looks like a structure that I show in the beginning solid right there. Not even earlier than in the example 1, it was that solid when I was introducing. But now there are many instances in your life, and I'm sure you will see this quite commonly. So let me bring it up on screen right here. All right, but so I am quite sure sometime in your the daily life, right there, sometime in your daily every day, you're gonna see this. What exactly is this? But this is a rooftop of a house before the construction workers put on the actual roof right here. But see, this is the concept of the slides right here. We have the base region is down here. Okay, this is the base region, and so in this picture over here, for this construction right here, then it's a simple base region being a rectangular shape, and then we have, these are the stripes. See, if we're looking straight down view over here, these are all the stripes. Okay, we put stripes over those stripes over our rectangular regions, and then on top, erected over the stripes right here, then see, these are the stripes, and then we have an isosceles triangle. And that's how it built the skeleton. I mean, it builds the main bones of the roof of a house. Maybe this is like a simple house or some part of the whole roof of a house. But see, this is a perfect example of of where you see a lot in your daily life about these concepts about the volume of one solid, but being generated by slices and slices, being accumulated by slices and slices like that. All right, and so. Tentatively, the plan now is that after this general discussion video lecture with the 2 examples here, I will provide other separate additional examples outside from this video lesson. I believe the 2 examples here are enough, but I will continuously provide more examples. But none of my students is required to watch through all of those, but the more you watch how I do it, the more you will learn, okay, and the more you will build your experience, okay. And so see you there at those other videos for the examples directly related to this volume by slices.